you very much for the invitation. Glad to be here. It's a great place, great meeting. Right, so I'm going to speak about something related to quantum computation and also related to a talk we had this morning already by Neme. And you'll see this is a coincidence, I didn't know about this beforehand. You'll see some graphics that will remind you of stuff we've seen this morning, and then I'll proceed. So all of you, I guess, know this, but since it's kind of important for what I'm going to say, I'll recall it. That on the fundamental level, physics is not described by the classical mechanics that we teach in school, but by quantum physics, to which classical mechanics is just a very coarse approximation, of course. And I'm illustrating here how we zoom into this quantum realm, and this graphics is taken from a different article than we had discussed this morning, but it's the same kind of phenomenon. This is a simulation that some people made on a computer. This is a computer simulation of an anyon gas producing vortices, and we'll come back to this. So the idea of quantum computation is to use the more fine-grained dynamics that actually governs physics at small atomic scales and below. And the idea is, going back to comments that Feynman and Manin made at the beginning of the 80s, that if we could manipulate matter, materials, crystals, say, on the atomic scale, that we could make use of that. And I'm kind of schematically illustrating this here by some process here. And we'll see this is actually an open problem, how to do this exactly, and even how to do it theoretically. And that's one point that I do want to talk about. So since a while back, a few years back, people have, the idea is old, it dates back to the 1980s. But more recently, people have gotten excited about the prospect of actually making this idea work of quantum computation. Ever since, there's this term floating around, quantum supremacy, which expresses, or is meant to express, the fact, or the would-be fact, that quantum computation should be enormously more powerful, not just a little bit, but many orders of magnitude, that it would go into a completely different realm than classical digital computation. So back in the 1980s, Feynman and Manin envisioned this by a simple argument. They just said, well, we know now very well by then, it was a 60-year-old insight, that there's all this extra fine dynamics happening on the quantum scale. So since physics and nature, hence everything in this universe, is actually described by these processes, then any simulation of them by a computer, say, which doesn't make use of this full fine-grained picture, but uses some coarse-grained classical mechanics, will necessarily lose in efficiency, just on general grounds. And more recently, this has been made more precise. That you can find discussions of how quantum chemistry, folding of proteins and stuff, is expected to benefit from computers that can actually resolve the fine detail of quantum mechanics, such as notably the interference that is lost when passing through the classical limit. And then even more recently, and this really triggered the excitement, it was found that beyond this sort of tautological application of quantum computation to simulation of quantum processes, it happens maybe counterintuitively application to combinatorial problems like database search, and notably to cryptography, concretely to factoring of integers into primes. So the general idea is, and I'm not going to speak about this much, but just to indicate why people are now so very interested in quantum computation, big money is flowing into it, is that it's understood that if you could build a quantum computer that's actually stable and robust, would actually allow you to run a programmable algorithm, and that's one point I'll get to, then it would be possible to break the existing RSA encryption mechanisms that currently run the world. And conversely, actually, you would then also be able to encrypt, with quantum randomness, and that would kind of, by basic principles of physics, give you unbreakable encryption. So that's one of the reasons why people are so very excited about it. And this excitement had led in the last years to a little race of various laboratories on the planet who have claimed that they have achieved or demonstrated some aspect of this quantum supremacy. It started with Google in 2019, and then IBM contested this, and then some laboratories in China, upped the ante and had ever more claims. And there's this race currently going on, but So far, all these demonstrations are contrived in that they do compute something that they set up a quantum machine that is hard to simulate classically, but it does something that you wouldn't want it to do if you weren't just interested in the fact that it's classically hard. They don't currently compute anything that is of practical use, and all of these demonstrations have been contested. There's now progress in classical supercomputers where people argue that they can actually reproduce many or most of these results. And the big problem here is that quantum computation, more so than classical computation, is prone to instability, to decoherence, and hence to error. So the theoretical descriptions of how it works so well, they all essentially assume that one is operating stably at or very close to absolute zero, so that you actually see the full quantum dynamics and no effects of the ambient classical bath. And that's the big problem. And this currently goes by the name, one says, okay, so quantum computers have been built. If you open the newspapers, you'll see the thing is reality, but all that has been built so far are so-called NISQ machines, noisy intermediate scale quantum machines that run for a few nanoseconds or microseconds and then decohere. So there's hardly anything you can program there. If, or as long, that is they're operated by sort of traditional means, so the means that are currently available. So the big idea, and that's where the topic of this conference comes in, of topology, is that topology might be a mechanism, or the mechanism, to stabilize quantum machines and make quantum computers actually be useful in practice. So retain their supremacy, if you wish, while defeating this problem of instability. This is an idea that goes back to a preprint by Kitaev already, now pretty much exactly 25 years back. And then a little later, there was this famous joint paper with Friedman and others on topological quantum computation, where they outlined this idea of doing quantum computation with anyons. We've already heard some of these terms this morning. I'm going to show a cartoon picture of what the idea is, how this actually works, or is supposed to work. It doesn't currently work. Because both the physics, like the experimental realization, but also aspects of the math of how exactly this is actually supposed to work have been left a little vague if one really digs into it. Maybe just to amplify this point of view, even though it may be obvious to some of you, but if you just follow the news, it might sometimes seem that the opposite is true. But here's a recent comment by a leading figure in the field, Urs Schreiber, who just 2 months ago or so in the MIT Technology Review said, the quantum qubit systems we have today are tremendous scientific achievements. That refers to these NISQ machines that Google and IBM and labs in China are running. But they take us no closer to having a quantum computer that can actually solve a problem that anybody cares about, right? That's what I said before. They do something quantumly, but not something that is practically useful currently. What is missing is the breakthrough bypassing quantum error correction by using far more stable quantum bits in an approach called topological quantum computing. So that's what I'm looking now at the theory of. So with Hisham Sati, we claim that we've recently made some progress on the theory side in a sequence of articles that we published. Maybe if I have time, I can say more about what we actually do there at the very end, just very briefly, but I'll keep this talk very expository. So I'll just give in the following now very general motivation, a cartoon motivation, and then very gentle exposition of what we're proposing, what we have done. So in order to do this, let me start now and step back and ask a super fundamental question. What is it actually to compute? This will be kind of important in a moment when we want to understand this, because when we're trying to understand what is it actually about a quantum computer that is so different. And so let me offer the following picture here. I looked around. One can find this, for instance, in Van Leuven and Wiedermann 2017. Essentially this, we give a more, how should one say, formalized version in this recent preprint. So to compute means we want to have some program and it's supposed to execute something. So this is it's super basic. What I'm saying here is kind of to set the scene for, we're going to boost it up to quantum computation. So the program is some loop of instructions that are repeated, and to execute means to send each instruction to some operation on some actual states, some actual physical things. And then the computation itself is to choose an initial state, let these operations, these instructed operations that are given by your program, act on it and see which result you get. And trivial as it may seem, if you take this diagram and say, well, what did we do here in more formal mathematical terms? then after a little reflection, you maybe realize that we're talking about certain pullback diagrams of fibrations. Whereas here the kind of the space of all operations on states fibered over just the operations. Here's the instructed operations, which if you do it right will be the pullback of this universal bundle. And we're asking for a path lift in that fibration. This is not important for what I'm going to say, not just to indicate sort of vaguely how there's actual theory behind what I'm sketching here. In particular, there's a formal language, homotopy type theory, in which to really put this on a computer, where this is then the univalent type universe and independent type family. Yeah, we can, if there's interest, we can talk about this maybe in the question session. Let me go ahead and just give you the most trivial example, and then from the super trivial example, we'll slowly get to the point of quantum computation. So it's a super simple program. So we want to go from some input to some output. The program that I'm going to show here as an example has a single instruction increase. So it's supposed to increment. Well, we have to say if we execute it, what are we going to increment? For the purpose of this example, let me say that we're acting on variables in F3. So in a finite field, in a finite ring, modulo 3, and we just, let's say we have 3 of these data types. We add 1 to each of them, mod 3. So it's just the same thing again. So we have a vector of 3 such integers mod 3, and we add. So to compute means, okay, we choose an initial state, for instance, the vector consisting of the values 0, 1, 2. We add plus 1 mod 3. We get this vector, which I've chosen such that, and this is just important for making the connection, that it happens to act as cyclic permutation on these 3 kind of data values. So that's a classical computation. And a point that is now important to realize as we go into the fundamentals of computation is that this looks very discrete, and you will maybe open a textbook on classical computation, and they will tell you this is obtained by discrete steps. But of course, in actual physical reality, if you put this on a computer, it's not a discrete operation. Fundamentally, all computation is along continuous paths, just for the reason that all physics, even quantum physics with its so-called quantum jumps, right, proceeds by unitary continuous transformations. So you can see this already, maybe best in the old computing machines. This is Leibniz's old machine. We actually have a crank that you turn in order to make it compute. It clicks every few turns, but it's still a continuous process. But also in modern electronic gates, if you switch on a transistor, it seems like it's just switching from 0 to 1. But of course, there's a continuous, ever so quick process actually happening. This becomes important because quantumly we cannot ignore that. So very schematically, if we just model the states of our computer by these 3 dots in some state space, which I'm not describing further, then as we compute, we actually trace out a path in the space of states. So this is supposed to remind you of that little computation we did a few slides before, where we just cyclically permuted these 3 data values. So such a cyclic permutation, could be schematically envisioned as being actually such a continuous path in the space of these configurations. And it would take you from this input value to this output value. Maybe I should have numbered them 1, 2, 3 here so that you can see that they're actually exchanged. And now the problem now is, as we now go to the fundamental physics, is that we want to reliably compute. Meaning that these operations that act here should be robust. Meaning that the result we get should actually be consistent. If we run the same program on the same input datum again, we do want the same output. If we don't, I mean, this is really the point of our modern digital computers. They always give the same output for the same input so that we can rely on this being the actual answer, not something that just happens by chance. So all computation needs to solve this problem that the result should be stable under small deformations of the composition path. And for this it's important that this is really a path. Let me illustrate this for the case of classical digital computation. So in classical digital computation, you essentially say, well, we don't know, we can't control these paths. So this is all our transistors going up and down in their voltage. We can't control this, but let's coarse grain the state space so that it doesn't matter where exactly our states are. So if when they start moving, that we still know in which bit they actually fall. So that's the idea. In a transistor, that's realized by the fact that switching it on or off actually moves thousands of electrons. So it doesn't matter whether there's 1 or 2 or 3 or even 10 or 20 electrons more or less. This is the width of these boxes, if you wish. As long as there is thousands, you say, okay, it's a bit yes. And if there's close to none, you say, okay, there's none. So it can happen, and it does happen from time to time, of course, that a classical computer does have an error. It's called a bit flip error. If one of these states actually moves out of its lattice, so this lattice is supposed to be a cartoon picture of the lattice you get by take 0, 1, the binary set, to the number of bits you have in your computer, but it's hard to draw. So this is one of the gates running out of its domain here. And as long as they don't, and usually they don't, you have a good computation. So this is stable. This is the success of classical digital computation, that it makes things stable, but it does so at the cost of brutally truncating the underlying physical process. So, powerful as our computers are, there's a whole lot of dynamics that you miss by just coarse graining this way. And so the idea of quantum computation is, specifically now, I jump over the standard explanation of quantum computation right to the topological case. The idea is, well, what if fundamentally we had physical processes that are actually fundamentally invariant under continuous deformations of these paths? So suppose you had such a process so that, it's a cartoon picture that I'm showing, so that the output would actually be invariant under deforming these computational paths. I'm drawing a very symmetric one here. Of course, this could be any one. That's the idea. So this would mean if you had this, that knots or links or braids, actually, depending on whether you close this up or not, would serve as gates, as computational gates, then called quantum gates. So the question then is, that's the idea of topological quantum computation, or in hindsight at least. So the idea is then, why and where do such processes exist? Is there anything in nature that has this property that we can move around its parameters continuously without it changing at all? And that's the interesting point, that the answer to that does seem to be yes, that does exist in the quantum realm. And the basic ingredient is, as the name suggests, of course, the quantization that gives quantum mechanics its name of energy. So as you all know, the energy is quantized. I'm showing standing waves here. The ground state of a free, so this would be some free particles, say in some boundary conditions here, the ground state is separated by this quantum of energy from the next excited state, and then so forth. And this property may, under good conditions, so this is for single particles, or essentially free particles. Now, if you move many particles together to make a crystal, then all the possible oscillations overlap, and these discrete energies form what is called bands. They form essentially continuous intervals of possible energies. But it can happen, it does happen, that you have a crystalline material where a gap remains between the ground states. So these are supposed to be the states that are inhabited by electrons, say, in a crystal, if it's absolute zero in the ground state, and then there can remain a gap. Say the gap may have some energy, delta E. And then we say, if that is the case, in an ordinary insulator, in an ordinary material, we'll say it's an insulating material. You put a voltage onto it, there's no current running as long as the voltage doesn't exceed this energy gap. Because right, by the quantization, you either take an electron from here all the way up, or you don't. There's nothing in between. That's the quantization of energy. But this means, so the key point here is that it does happen that, so that this gap remains, so that we have an insulator. And some of these insulators, I'll come to this, have this topological property that they're topologically non-trivial. But so let's just sketch the idea. So if you have such a material that is an insulator in this way, then it means that as long as you perturb it, maybe to operate on it with some quantum gates without exciting that gap, then as long as that will be the case, you have a topological phase. It will have that property that small deformations, where small means delta E, do not affect the ground state at all. Now this alone isn't, this is sufficient for stability, but this is not sufficient to have something interesting. To have something interesting, you now need that this ground state is interesting, not just the single. And that's where my question from this morning relates to. So we next need that ground state in order to have a decent quantum computational device, that ground state to be degenerate, as one says. So it has to be, a Hilbert space has to have dimension greater than 1. And in particular, if we do want to operate on it in the sense of moving stuff around, it should have, and this is again a cartoon picture, this is not really what we expect to see in this crystal. But if in this ground state, we can imagine we have certain defects, say vortices, and the ground state depends on them, then we can now ask, well, what happens as we slowly move these defects around? that will operate on this quantum ground state in a robust way, and we would have a substrate for quantum computation. So then we led to this picture here, where so this is supposed to be, suppose that we have a crystal that's effectively 2D. For instance, graphene is an example of such a quantum material. Suppose you have some defects in there, and slowly, in order not to excite that energy gap, the technical term is adiabatically, you move these points around. Since everything is topological, as long as you don't excite that gap, nothing will now depend on the exact position of these points, except that globally, for instance, if you move them once around, you may get from one state to another state in the degenerate Hilbert space of ground states. So that was the original idea of topological quantum computation by Kitaev, Friedman, and others. And if we put it into this schematic or this formal picture of path lifting, then it means now that a program is now a braid, an open knot, if you wish, which prescribes how we're moving these defects around each other. And to execute it means to actually move them around in some actual material to see how it acts on the ground state Hilbert space. Then you pick an initial state and ask where it goes to. And the point is that you get now a linear transformation from input states to output states, which is a quantum gate, which is, if you do it right, or should be, ought to be, that's the idea, independent of little perturbations of these paths here, which are inevitable. Yeah, this is just a technical remark. If you actually implement this, there's certain classical names for these fibrations that one gets here, which is kind of important for actually implementing this. So the question then is, so that's the kind of quantum materials we would be asking for. They need to have this gap, and they need to have some way of putting defects into them, such that the ground state non-trivially depends, say, on the position of these defects. So such materials with these properties have come to be called topological phases of matter. It's essentially what I just shown, for instance, crystals with this gap, where the class of the valence bundle in which the electron wave functions take their values may be non-trivial. So this is, I think this was mentioned this morning, the existence of topological phases of matter theoretically and then also in practice. A few years ago was a big success, led to a Nobel Prize of a few people actually realizing this in the lab. But then we need one step more on top of this. We need that the ground state is non-trivial. So there are some topological phases where the ground state is sort of just a singleton state. So at most you can act with an abelian phase on it, which is not enough to do universal computation. So a name introduced by Wen already long ago, and then more recently become fashionable again, is that we say that the ground state exhibits topological order if, even at absolute zero in the ground state, there's non-trivial structure in there. And then we say if there's point defects now in a codimension 2 fashion, then we call them anyons. So there's some early work on this by various people. So such materials are expected to exist. So I'm talking now about topological phases that do exhibit topological order with non-abelian anyon phases. But the CDA has remained somewhat elusive, both experimentally as well as theoretically. So on the experimental side, there has been a huge amount of effort to produce an incarnation of these things that goes by the name Majorana zero modes. And after a lot of excitement throughout the last 10 years, starting in 2010, it seems various articles have had to be retracted. Various other articles are under scrutiny now. So it seems one can say safely, this approach has actually failed. These Majorana zero modes seem to be not there. More recently, people have noticed, that's the point that's kind of important for the details that I'm talking about, but maybe not showing here, that we can get away from this picture of braiding in momentum space, braiding actual positions, and maybe we can ask for braiding in momentum space. So suppose you have a two-dimensional material, a crystalline material, or just any material, then you can Fourier transform the states of its electrons, say, to the momentum basis, where the variables are no longer their positions, but their wave vectors k1, k2. And then there's a very you know, the quantum mechanical formalism doesn't care much about whether you work in position space or momentum space. But the interesting thing is that in momentum space, there is a well-known, well-understood, and actually well-controlled notion of point-like defects that exist. These are called band nodes. So remember these energy bands that I briefly mentioned at the beginning. If you have a crystalline materials, then the energy of the electrons appears in bands, as it's called. And it can happen, this is the case of what's called topological semi-metals. It may happen that these bands are separated by a gap most of the time, except on certain points, codimension 2 points, where they have a node, as it's called, where they touch at this point. So if you look at the math that describes this, you notice that now in momentum space, these nodes behave like defects, like sources, for instance, of Berry curvature, delta sources of Berry curvature, sitting here. So in momentum space, it appears as if these are point-like defects. And you can ask now what happens as you braid these around. And in fact, you can do this, for instance, by exerting strain on your material. You know, you change the Hamiltonian, you change where exactly these nodes appear. And people have, so there's a bunch of reference here. Yeah, these slides are online. All these underlined things are hyperlinked to the actual references here. So people have argued that it should actually be feasible to braid these nodal points around. That's one thing maybe one should look at on the experimental side. So theoretically, the issue was this. There was a highly successful mathematical description of topological phases, which goes back to Kitaev's article and has then been developed by several other people. And it effectively says that there's some version of topological K theory, of the exceptional generalized cohomology theory called topological K theory, that characterizes the possible topological phases that a given crystalline material can be in. I'll say a bit more about this if there's time at the end. The issue with this was highly successful for the so-called free non-interacting phases. So it does very nicely classify topological phases of matter that do not contain topological order, that are not strongly interacting. And this works so well that people, even though it's not really implied by the math, but that people implicitly deduce from it working so well for the free case that K theory cannot be the answer to what classifies the interacting topologically ordered phases. And so instead of trying how to push K theory to the interacting case, people kind of threw it in the wind and tried all kinds of other things, somewhat at random. So this is the point we're making in this article, that we say, actually, let's keep the K theory. We need to add something else. And let me indicate what that something else is. So here's the picture. I'll try to establish, I'll show you the dictionary, starting with the well-established stuff on the physics underlying, topological order, and hence topological quantum computation and the theory controlling it. So all the way back, I already indicated this at the beginning of crystallography. We understand that, or its quantum version, we understand that electron states, the momenta states, are given by points in this dual torus of wave vectors in our crystal. And yeah, so this would be something like this. And then this proposal, going back to Kitaev and developed more mathematically by other people, then says that the topological K theory, so some generalized cohomology of this torus, captures the topological phases, the deformation classes of topological phases of these valence electron states. Let me try to indicate very briefly the math, or the connection between the physics picture and the math that makes this arrow here work. So the idea is this torus, this Brigand torus. So this is I'm always looking at effectively two-dimensional quantum materials here, like graphene. So that's why it's T2. So it means a dual torus. It's the space of possible quasi-momenta that an electron can have in this crystal. And so the idea is that at each point of this, at each momentum, there is some Hilbert space of electron states, so-called Bloch states, electrons with that momentum. There's also, since these are fundamentally relativistic particles, there's also a corresponding space of positron states. And one can arrange it such that from the full Hilbert space of all possible excitations, that the valence electron states and the Bloch states are picked out by a Fredholm operator by a bounded linear operator whose kernel in this graded Hilbert space is the electron states, whose co-kernel is the positron states. And so the idea would then be that for each point in the Brion torus, we have such a pair of vector spaces of electron states and of positron states, which actually lifts to a Fredholm operator that picks these spaces as kernel and co-kernel, so that in total we get a continuous map from the Brion torus to the space of Fredholm operators, suitably topologized. And homotopy classes of such maps are famously one model for this cohomology theory called topological K theory. So then that picture alone, you can easily see, can't be the full story, because the topological K theory just of T2 itself is just not rich enough to capture a lot of physical structure. And the key point that is missing in this picture, or so far, is the fact that we're not just dealing with a plane, just this plane torus, but there's a point group of the crystal structure acting on the Hamiltonian, and there may be further internal symmetries. So there may be a group, discrete group of quantum symmetries under which our Hamiltonian is invariant, and such that all possible deformations of it, say as we exert strain or other external forces on our material, preserve that symmetry. And I mean, if you know the mass, then evidently, otherwise by some arguments, the mathematical reflection of that on the side of K theory is that we somehow have to move from just plain topological K theory to what's called equivariant K theory. I can indicate this if you allow me to use this notation here, which is really a notation for moduli stacks, but it's maybe intuitively accessible what's happening here. So we have this group G acting on our Brion torus, say by point symmetries, and we can form this double slash here, double dash is supposed to indicate not the plane quotient, but the homotopy quotient that turns this torus into an orbifold by this group action. So it's some kind of enriched space where we remember this group action, including its fixed loci and its automorphisms it may have, and that's kind of crucial for this to work. And then we don't, from this, we don't, yeah, I mean, okay, there's some arguments going into this. We don't no longer map it quite to the space of Fredholm operators itself, but to its homotopy quotient by the canonical group that acts on these Fredholm operators, which is the projective unitary groups acting by conjugation by unitary operators. Both of these groups map to the classifying stack BPUH. And if you have maps that respect this projection, they are representatives for equivariant K theory classes. So that's, if you know some stacky language, that's the sort of immediate formulation or implementation of quantum symmetries into this picture of valence states of electrons and positrons. So this says that, okay, so crystalline topological phases with that are symmetry protected, as the solid state physicists would say, are supposed to be classified by the equivariant K theory of the Brion torus. So that was the state of the art sort of around 2013. And all this applies to free phases, because these electrons here, they just fill up the ground state. They don't, the formalism doesn't see them interact with each other. So that's this first proposal we made. I mean, this didn't just fall from the sky. Maybe if there's time at the end, I can indicate a bit how we actually arrived from this. It's via some arguments in string theory, actually using defect branes. But the final answer for this case of defects in a crystalline material, one can actually intuitively see how this answer makes sense. Namely, we replace, so our torus, think of the torus as being a quotient of the complex plane. And I'm writing this complex plane now. So instead of just looking at electrons that are parametrized over this torus, which really just means I'm looking at a single electron, one point in the torus is the momentum of that single electron. Now I'm asking instead, let's replace this by the space of configurations of distinct points in C. So this is a cartoon here with some extra decoration, which maybe we'll talk later about. Focus on these points here. So this is meant to be, this configuration space is meant to be the space, topological space, suitably topologized, one of whose elements is a configuration of points. In this example, it's 3 points in the plane that are distinct. So as you move around these points, as you move around in the space, you see these points move, and you can maybe envision how such a movement of points, if they would now move around each other, actually produces such a braid, which is what we want to use as a quantum gate. So the idea is that a vector bundle over this configuration space is now actually the suitable home for wave functions of triples, in this case of triples, in general of n tuples of electrons, and harbors the interacting quantum wave functions that are usually constructed from Slater determinants. So this has the potential to encode interacting electron states. And then it turns out that on this richer space of configurations of points in the Brillouin torus, there's also more interesting twists of topological K-theory, which I'm not showing currently, but you just have to believe me. It's a richer space. Turns out there's a new extra twist, new extra map to this classifying stack that is available there. And choosing that appropriately turns out to encode, we claim. So that's just a bird's eye view, anyon species and anyon wave functions. Such that you finally arrive at this picture again, but now as the illustration of a mathematical theorem, namely these twisted equivariant K-theory classes on the Brillouin torus will now form a fiber bundle as the points move in the configuration space. There's a canonical connection on this fiber bundle called the Gauss-Manin connection, in this case on twisted equivariant K-theory. And with this Gauss-Manin connection, you can now let these points move and ask how your K-theory cohomology groups change. And then you can interpret the elements of these K-theory cohomology groups as ground states. In fact, we prove there's a map, there's an embedding of the space of conformal blocks, which I very briefly mentioned a few slides ago, that is thought to harbor the actual anyon wave functions. And you can see how these actually move. So we arrive at this picture. This was on the left, the physics picture that was kind of sketched out by Kitaev, Friedman, and others over 20 years ago. So this is based on a preprint that's actually quite a bit older. Someone says, okay, this topological quantum computation should somehow be based on anyon braiding in topological phases of matter exhibiting topological order. And there was no coherent mathematical way of saying what all of this together, so there were bits and pieces known, what all of this together actually means. And so this proposal, this result we have would actually say, yeah, so this is modeled by Gauss-Manin connections on twisted equivariant differential topological K-theory of configurations of points in the Brillouin torus. And so the claim would be that this actually leads to a very concise theoretical mathematical formulation of what's actually going on with anyon braiding. And so there is a perspective now of putting this on an actual computer, because there's computers who implement this homotopy type theory that I mentioned, which in turn implements these vibrations that I've shown, in terms of which one can implement these Gauss-Manin connections, actual computer language, to get kind of a quantum simulator that actually reflects not just the general principles of quantum computation, but actually those of braiding of anyons. So I was invited, I think, to advertise, and that's what I'm going to do now, that we just started actually a new research center at New York University branch in Abu Dhabi, which is going to be concerned with developing this approach. It's called the Center for Quantum and Topological Systems. So NYU Abu Dhabi, yeah, they have a branch there. With Hisham Sati, we're there, and we have a, so this just started recently. We're just this week, in fact, just these days that I'm here, the first of our hires are arriving in Abu Dhabi. Hisham Sati is the main PI of that center. There's further computer scientists and solid state physicists from the NYU network involved. These are our new postdocs. We're just arriving these days. While I'm here, I have to rush back to Abu Dhabi to help welcoming them. And yeah, so there's some general effort in the Emirates to push in this direction. There's lots of interaction we have with the center. In particular, there's a branch of New York University in Shanghai where they're developing quantum technology, doing some actual Bose-Einstein condensates, some NISQ quantum computing. There's a, in New York itself, Center for Quantum Phenomena, is concerned with solid state physics. And there is, last but not least, the TII Institute in Abu Dhabi, actually currently in the process of installing one of these NISQ machines, one of these quantum computers in the Emirates. So what's the point? The point is that with the new center, so this gives a good background of general quantum computing infrastructure potentially. So we want to kind of help out on the theoretical side and bring in some topology now to this endeavor of setting up robust quantum computation. And so if I understand well, I have 15 minutes left. Is that right to talk, or should I stop? So if there's some time left, let me step back and say a bit. So I indicated without giving any details, I indicated the kind of math claim we're making regarding these anionic phases of matter. Let me actually indicate how we arrived there from analysis of structures in string theory. So it's you may have heard, I'm sketching now a folklore that has been going around the scientific community for maybe 3 decades now. Not all of this is equally well known, but many things are. And I'm recalling this, and then I will point out that it has, in fact, to a large extent, been folklore and has been waiting, for an actual math to make it precise. Anyway, there's this parallelism where topological K-theory, in its fully twisted and equivariant and differential form, which means certain things, classifies 2 things in physics. On the one hand, and that's what I've talked about, and I tried to motivate it a little bit with these maps, these homotopy class of maps to the space of Fredholm operators. It was known or understood. I mean, this was really not a theorem in any way. It was a hand wave, even for physics standards, a hand wavy argument that it classifies these 3 topological phases in condensed matter theory. On the other hand, even earlier, it has long been argued that it actually classifies stable d-branes in string theory, right? So in string theory, you assume that fundamentally all particles are secretly little one-dimensional strings that zip around. And then it turns out if you analyze this, there may be certain high-dimensional defects in space-time on which these strings may end, of course, the d-branes. And a long argument, or not so long argument, a long discussion at least, which is widely accepted, even though it's hand-wavy, argues that topological K-theory also classifies these stable d-branes. And another part of this folklore is that great as these 2 items are, they are in need of an enhancement. So on the topological side, this was understood much more recently, but it's much more evident there. Well, if this is just 3 topological phases, there needs to be something that enhances this to the interacting case, the case that's actually supposed to harbor these non-abelian excitations that we care about. Much earlier, and by very different arguments, around 95, famously it was argued that in string theory there's some non-perturbative effect, or a whole set of effects that needs to be taken into account, because the string theoretic argument is all just perturbation theory. So on the left side, this is what takes us from this interaction is what takes us from 3 topological phases to what's called topological order. And here on the right side, this is what would take us from what people call d-branes to actual branes in M theory. So that's this non-perturbative aspect. And the idea was that, having these, or that one needs this in order to, for instance, on this side, find these anyon statistics, these anyons, and that would be needed for topological quantum computation. But also on this side here, often forgotten when people talk about quantum gravity and all these things, it's this non-perturbative case here that one actually needs in order to realize realistic quantum field theories like actual QCD in string theory, which, under duality is actually strongly coupled in the bottom. So that's a folklore that has been circulating more or less famously for a long time. And so long that if you look at many of these references, many of these participants in these communities at some point start to behave as if these things are all settled and all known. But it's maybe important to realize that the full mathematical definition of K-theory in this fully-fledged case, where it's twisted and equivariant differential, has actually never been constructed before. This year had famously remained open. It's really this M theory conjecture. And it's this bottom case, kind of where you need the solutions to these top cases here, which is the case that is actually relevant in practice. So we had been working on this question on this side, and over the years, suggested solutions to these three problems. And then kind of noticeable that, well, we said, okay, if we have the solution here, then we have the solution here. That's how this proposal came about. So there's some, yeah, if you look around our articles, you'll see there's some general mathematical theory called cohesive infinity topos, where we claim this fully twisted equivariant differential K theory is naturally constructed. This is just a technical thing. More, how should I say, in need of more creativity is this proposal here for what it is that actually has replaced, that brings in these non-perturbative effects. And this is where these configuration spaces and multi-points come in. So this is something that goes back to an idea that Hisham had many years back. And in honor of this, it's called now the hypothesis H for Hisham or homotopy. And then combining this leads to this concrete implementation of topological quantum gates in twisted equivariant differential K theory that I tried to indicate. So that's the way we arrived. And I have more details now on how this works, but I see the countdown is running now. I could stop here and maybe we check which questions there are, and then I can reply to these. Thank you.